Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is a simple code generator. A code generator generates target code for a sequence of 3 address statements and effectively uses registers to store operands of the statements. Here input to the code generator is the 3 address statements. 3 address statements are in the form x is equals to y, op, z. OP is any operator, X, Y, Z are the operands or addresses. So, we have register and address descriptors. Register descriptor is used to keep track of what is currently in each register. What is there? That is which value is stored in the current register. The register descriptor shows that initially all the registers are empty. The address descriptor keeps track of the location where the current value of the name can be loaded, can be found. Location may be a register, a stack location or memory address. A code generation algorithm. A code generation algorithm. For each 3 address statements of the form x is equals to y, op, z, perform the following actions. We have 3 actions, 1, 2, 3, 3 steps of the algorithm. So, for x is equals to y, op, z, the equivalent to assembly code will be move y, r1 operator z, r1. Here r1 is a register. So, registers are limited in number and also the size of the register is compared to memory is smaller and faster. So that we prefer to use registers than the memory. First operation, move operation, we will move the value of y to a register r1. Then perform operation on z. Operation may be any addition operation, multiplication operation, sub operation, any operation on z, that is op z, r1. The operation on z with the content of the register r1. This is the equivalent to target mission, that is assembly code for the given 3 address statements of the form x is equal to y, op, z. The first statement, invoke a function get register function, get reg function to determine the location L where the result of the computation y, op, z should be stored. Here x is equals to y, op, z. The computation of y, op, z is stored in register x. Variable x. So, the result of the operation y, op, z will be stored in the location L. So, get reg to determine the location L where the result of the computation y, op, z should be stored. For this step 1, we need to consider 4 options. Get reg register. First one, if y is in register, that means the content of y is a variable is already in a register, some register, no need of this operation, move operation. So that y is no more needed. So, y is no more needed. That is one option. First option is for get register function, if y is already in register, that is value of y is register, some register, no need of moving the value of y to r1. So, y is no more needed. Second option, y is not in a register. If y is not in a register, then return a register. If registers are available. So, first option is y is in a register already there. So, y is no more needed. Directly we can perform the operation op on z. Second option, if y is not in a register, so that we need a register. If the registers are available, the get reg function will return a register. That is second option. Third option, if y is not in a register but and registers are not available. Registers are not available. Registers are not available. So that the get trig function will move the contents value of some register, move value of some variable, value of some variable which is already present in the register, which is already present in the register, which is no more needed, which is no more needed, which is no more needed to the memory. That means if y is not in a register, we want a register, but registers are not available. At that time, what we will do? We will move value of some other register which is already present in register, but the value of that variable is no more required, so that we will move that value of the variable to the memory location, so that we vacate this one of the registers and allocate that register for y. Fourth option. The fourth option will be, there is no register, that is y is not in a register. If y is not in a register and there is no register, there is no register to move data to the memory. That is, all the registers are busy and all the variables stored in the registers are needed, so that we cannot copy content of some of the variables into memory. So, at that time the last possibility is we have to move, that is, we have to store the result of YOPZ into memory location. Store the result of YOPZ to memory location. So, for first step, we have four options. Invoke a function getReg to determine the location L where the result of the computation YOPZ should be stored. For that, if y is in a register, first option, y is in a register that is already there, so y is no more needed, so we need not to perform move operation, move y comma R1. Then second option, if y is not in a register, so that we need a register. If the registers are available, getReg function will return a register. Third option, if y is not in a register and the registers are not available, so that we can move value of some variable which is already present in a register, which is no more needed, to the memory location. Fourth option, if y is not in a register and there is no register to move the data to the memory, so that all the variables are needed, value of variables stored in the registers are needed, so that required, so that we cannot move the data to memory location, so that we have to move our result YOPZ result, the result of YOPZ to the memory location. Second, consult the address descriptor. Second step, consult the address descriptor for y to determine y dash. Y dash is the current location of y. Prefer the register for y dash if the value of y is currently both in memory and register. If the value of y is not already in L, generate instruction move y dash comma L to place a copy of y into L. That means, if the value of y is not in a register, move value of y to a register. We need this instruction, first instruction, move y comma R1. Third step, generate the instruction OP Z dash comma L, where Z dash is the current location of Z. That is, prefer a register to a memory location if Z is in both, that is memory and register. Update the address descriptor of X to indicate that X in location L. If X is in L, update its descriptor and remove X from all other descriptor. That means if the value is in both register and memory, we can perform directly OP operation, that is any addition, subtraction, multiplication operation. Second step, perform OP on Z, R1. After performing all the operations, if Y and Z are no more needed, free up the register. That is the fourth step. If the current values of Y or Z have no next uses, are not live on exit from the block, that is basic block. At the exit of the basic block, Y and Z have no use, so that they are not live, so that they are and are in registers. Alter the register descriptor to indicate that after execution of x is equal to y op z, those registers will no longer contain y and z, that is will free up the registers. This is about code generation algorithm. Next, we will solve one example, that is generating code for assignment statements. The assignment statement is d is equals to a minus b plus a minus c plus a minus c. Might be translated for the following three address sequences. So, this is the given expression, d is equals to a minus b plus a minus c plus a minus c. For this, we will write a three address code like this. I will take first temporary variable t is equals to a minus b. So, one operator minus three operands, t is equals to a, b and t are the addresses, three operands, one operation, op is the minus. Then the result of a minus b is stored in t. Then I will take a temporary variable u, that is u is equals to a minus c. For this, a minus c, operation, the result of a minus c is stored in u. Then after that, u will contain a minus c, t will contain a minus b. So, a minus b plus, now we have to evaluate a minus b plus a minus c. A minus b is available in t plus a minus c is available in u. So, t plus u, the result will be stored in temporary variable v. Then after that, add a minus c to v. So, a minus c is available in u. So, v plus u, that is v is a minus b plus a minus c plus u means a minus c. The result will be stored in d. Now, d is live at the end because d is storing the result of total expression. Then, assembly code statements for these given three address statements. The three address statements are t is equals to a minus b, u is equals to a minus c, v is equals to t plus u, d is equals to v plus u. First statement, t is equals to a minus b, that is three address statements. The code generated for this statement, three address statements t is equal to a minus b is, first we will move a to a register r0. r0 is a register, a is a variable. The content of a is moved to a register r0. After that, second instruction, subtract b from r0 because r0 will contain a. So, sub b comma r0, b is subtracted from r0, the result of subtraction will be stored in register r0. So, that the register descriptor tells the r0 contains t, which register contains result of the expression. r0 now containing result of t, t is what? A minus b. Address descriptor, descriptor means which value of variable stored in which register. So, t is in r0, t is in r0. For the second three address statements, u is equal to a minus c, u is equal to a minus c. So, move a comma r1. See, a is a variable, r1 is a register. See, we should not use the same register r0 because r0 containing a minus b, that is t, r0 containing t. Here, if you use r0 instead of r1, what will happen? The r0 replaces t. That means, we in the third statement we are using t. So, while executing third statements, we need to use r0. r0 we need r0. So, that here we should not use r0, we should use another register 1. So that move A to a register R1. Then subtract C from R1, sub C comma R1. Now R1 contain result of A minus C. So R1 will contain U, that is result of A minus C is U. R1 will contain U, and R0 as usual still containing T. Now T is in R0, U is in R1. Next, third statement, V is equals to T plus U. V is equals to T plus U. Now we have to add T and U and store result in V. Add mnemonic add R1 comma R0. R1 containing U, R1 containing U, and R0 containing T. So T plus U. Adding T plus U and result will be stored in R0. R0 containing what? V. Result is stored in V. So variable V containing T plus U. So R0 will contain V. R1 will contain as usual U. So R1 is not updated. So R1, the value of R1 containing U, that is subtracted from R0. R0 containing previously containing R0 containing T. So T plus U added and result will be stored in R0. R0 containing V. Now U in R1, V is in R0. Next, final U plus V added and result is stored in D. So adding V and U, add, where is U and V available? U available in R1, V available in R0. So that add R1 comma R0, R0 containing result, that is D, R0 containing result D, and after that R0 containing result of V plus U, that is D. So finally we will move R0 V plus U to the register variable D. So finally R0 containing D, and D is in R0 and D in R0 and memory also, because we are moving value to a variable, value result of R0 we are moving to a variable is available in memory. So that D is in both R0 and memory location. Like that we can generate a code by using code generator algorithm. Thank you.